Yeah, so if you go to Brightspace of this week, you can see I posted 3 code. One is called LUP. So that is actually LU decomposition with pivoting. So it returns you 3 matrices: the lower triangular matrix L, upper triangular matrix U, and the pivoting matrix, the permutation matrix P, such that P times A equals to L times U. So this code, so this LU decomposition with pivoting actually requires, I guess I kind of erased the part. So it does a lot of, so it's an implementation of the proof like we have. So it does a lot of that one step LU decomposition. So that is to factor matrix A into 2 matrices, the lower triangular matrix times some matrix that has a bunch of zeros in the first column. So that's what LU one step does. And what this LU with pivoting does is basically like it run through like all the different n and then perform a lot of this one step like LU decomposition, so that the matrix you're working with each time becomes smaller until it goes to 2 by 2. So with that, I can implement like the forward substitution and backward substitution. And then I can put together a solution for any linear systems. So this is the example we had before. This is like 3 by 3 matrix times x equals to this b vector. So if I run it, I should get the same solution as before. I believe that's 1, 2, 3. So this theoretically, this is a solver that can work for any non-singular system. So here, one quick thing you can try is that it's something we tried before. So I can let the A matrix to be a random matrix of n by n, and the right-hand side B to be a vector of n by 1, and then try to solve AX equal to B. So this thing, as long as A is non-singular, I should be able to find a solution. And with different n, I want to test how long does my code run. So for example, now this A is 500 by 500. So if I run, so I put a little timer in my code, you see it takes 0.75 seconds. But now let's say this n is 500. I want to turn it to be 1,000. So it's twice the size of the matrix. Then with the estimation of the number of operations here, what time it should take? See here, the n is already large, so pretty much the number of operations is dominated by this term. Now n is doubled. Then how much does the operation number change? So n becomes twice of itself. How many operations do you need right now? 8 times, right? Because it's n to the power of 3. So if n is doubled, then the total number of operations become 8 times of itself. My computer runs at a constant speed. That means the amount of time it takes should be 8 times if I change this n into 1,000. If I do that, the new time is 5.66 seconds. So what is 5.66 divided by 0.75? It's 7.5. It's not 8 yet. So this kind of scaling works better and better when n gets large. Now if I run it again with 2,000 times 2,000 matrix, then how many seconds do I need? So here, before I need 5.66 seconds. So that times 8 will be 40 seconds. So it's gonna take a while, but we'll see if it eventually takes 40 seconds. So you see, that is why the complexity of an algorithm is important, because once you know the complexity of an algorithm, it gives you a sense of how much time you need to spend. In this case, the complexity is n to the power 3, and it is actually kind of hard to improve beyond this point. You see, we're trying to solve a linear system. We're trying to solve AX equals to B. If A is n by n, you need to do the complexity is like this much for you to solve the system. So it turns out how to improve this. This is a big topic. Can you do things even faster? It turns out in general you can't. Because if you want to do things even faster than this, there are 2 options. You might either get a solution that's not so exact. So say you reduce some precision, there might be ways to make the computation faster. That's one way to do it. And there's another way to do it, is that sometimes this matrix A has certain structures. You see that it's 46 seconds, so it's completed. So it's 46.6 divided by 5.66. Should be close to 8.23 times. So it's almost 8 times now. So overall, you cannot, when you do the algorithm composition, you cannot really escape this type of complexity. So each time you deal with the system bigger, like the amount of operation needed grows with n to the power 3. But like I said, sometimes this ax times equals to b, if you don't want to solve it exactly, it is actually possible to reduce the amount of work to O n squared. So this is a big improvement for large n. So the complexity drops dramatically in this case. So instead of n cubed, we deal with n squared. And with certain structure of A, actually you can do, well, there's an algorithm, like one of the most famous algorithm of 20th century called fast Fourier transform. If you do fast Fourier transform, it is actually possible to solve the system with a complexity of n times log of n. This is way bigger of an improvement because log n, this function grows very slowly. N equals to 100 log n is 2, and then let's say 10 base log. So if n is 100 log n is 2, if n is 1000 is 3, so it grows very slowly and then comes in. So that's why this fast Fourier transform of FFT is such an powerful algorithm, and it's one of the most famous algorithm of the 20th century. We will not cover any of that, and pretty much the take-home message here, you don't need to do the whole calculation of how many steps you need. You need to remember that for LU decomposition, the complexity is n to the power 3. So you can expect how long your code, how long it takes for your code to complete. Okay? And that's it for this week. And definitely make sure to play with the code. I'm pretty sure, when you read the code, some steps might be kind of not so trivial. But if you have any questions, feel free to ask us during recitation and office hours. Okay? That's it for the week, and I'll see you guys on next Monday.